Hello and welcome once again for another ES340 video. This is an extra example problem for day 7. Air is contained in a piston cylinder assembly and undergoes a power cycle as shown above. So here's the cycle. We have values for pressure. This is 5 bar. This is 3 bar. Obviously this is 3 bar. This is 5 cubic meters per kilogram. This is 1 cubic meter per kilogram, right, because this is the specific volume. And we know something about its isothermal here, and so on. Okay, so we want to assume that it's an ideal gas, and we want to evaluate the thermal efficiency. Well, recall that the thermal efficiency, eta, is equal to the work of the cycle divided by Qn. Okay, and we can identify the work of the cycle in a variety of ways. Or we can also set this, of course, there's another way of viewing this, which is 1 minus the heat that went out divided by the heat that went in. So we can analyze this in a couple of different ways. Now note for process 1 to 2, this is isothermal. That is, T is constant for this process, right? Isothermal means T is constant across the process. So if I look at my ideal gas law, I see that PV is equal to RT, but T is a constant in the process. And why is that important? Well, what that means is that RT is constant, because R is also a constant throughout the process. So that means that PV is equal to a constant. You've seen this before. This is a special kind of process that we've seen multiple times already. And that means that P is equal to some constant, we'll call it C, over V. Okay? Where C is, of course, just equal to PV. So if I do P1 is equal to 5 bar, and V1 is equal to 1 cubic meter per kilogram, which is what I can read off of this chart here. 1 for V and 5 for P. And then what I can do is I can find that constant C. C has to be equal to let's put this as 5 times 10 to the 2 kilonewtons per meter squared times 1 meter cubed per kilogram, which means that it's equal to 5 times 10 to the second kilojoules per kilogram. Just makes our work a little bit easier here. So we can actually use this to our advantage to find, and this again is because it's an ideal gas. Obviously, if it was not, we would have to say find Z, for example, the compressibility factor, or we would have to go to the tables, right? So these are 3 different ways of doing it. We can assume it's the ideal gas model, and use that fact to help us work through these. We can use the compressibility factor, which gets more accurate than the ideal gas model. It's a very similar model to it, just now we have Z that could be non-1. And the final thing, of course, the most accurate is actually to actually take the measured values, which is what we're doing when we do the tables. So we can have those different situations. Okay, But we were allowed to assume that this is an ideal gas here. So the work from 1 to 2 is, I'm sorry, actually this is the specific work. I'll give it a lowercase w, because notice we have this in kilojoules per kilogram. So this is really going to be the specific work that is done. And that's going to be equal to this C, which I'm going to pull out of the integral, 5 times 10 to the second kilojoules per kilogram, times the integral of 1 over v, lowercase v here, d lowercase v, from v1 to v2. Okay, so this is equal to 5 times 10 squared kilojoules per kilogram times the natural log, in this case it's going to be a v2 divided by v1, if we want to obviously go that route, which is equal to 5 times 10 squared kilojoules per kilogram times the natural log of, what was the volume? It was 5 V2, this is V2 over here, 5 cubic meters per kilogram. I'm not going to put the units because they're going to end up canceling each other out as I divide them. Over 1, that was what the initial one was up over here, cubic meters per kilogram. So that's the natural times the natural log of 5, and this comes out to be about 804, because this is 500, right? 804.719 kilojoules per kilogram. Now we have to go to the energy balance equation for this. Again, this is the specific work, just be careful there. Because this is really W12 over M is equal to W12. And if we go to the energy balance equation, again, we're going to ignore the kinetic energy and potential energy effects. So it's probably getting a little bit much for me to write these over and over again. So I'm just going to assume that you remember the energy balance equation. We could have to include the kinetic energy and potential energy in certain circumstances, but only if it's clear in the problem that we need them. And I'm going to give this a lowercase q1 to 2 and a lowercase w1 to 2 because this is the specific quantities of each of these, because we don't here I'm working with the specific work, so it's just going to be easier if everything is in terms of the specific quantities. And so for this problem, we should figure out what the change in internal energy was, but there is no change in internal energy. There was nothing given in the problem that would indicate that that there was any change in internal energy. So we know delta U is equal to 0, which just implies that Q1 to 2 is equal to W1 to 2, lowercase, and that's equal to 804.719 kilojoules per kilogram. Right? If I scroll up here, there's no indication of any delta U, which they would give sometimes, but there's no indication there that there is any delta U in this case. And this should be, I should label this as delta U1 to 2, just so that we keep that in mind, because we're going to have different scenarios here. Now, what about from 2 to 3? Okay, from 2 to 3, we have a compression here, obviously, so we have a change in volume again. So there is going to be some work, and it's going to be negative because it's a compression, right? This is one way that we can have a sanity check. The work is going to be negative because the volume got smaller, compression. So if we don't come up with that the work is negative, then we know we did something wrong in the computation. Always good to think about those things. Okay, so for 2 to 3, what we're going to do is note that we have, for this particular problem, we have constant pressure, right? The pressure is constant at 1 bar. Since P is constant, we know that if I do the integral, right, integral of P dV is going to be equal to P times the integral of dV, because P is constant. And the constant was at 1 bar, which is 10 squared kilonewtons per meter squared. It's also kilopascals, right? We call this unit as well kilopascal. Okay, and so that means that P delta V basically is going to be my work. Should be V2 to V3, V2 to V3, and which is equal to 2 to 3, which is equal to P times V3 minus V2. So I should come out with a negative value here. So we know that this is going to be 10 squared kilonewtons per meter squared times, well, let's go up here. This was 5 meters cubed per kilogram, and then it went down to, as I'm going this way, it went down to 1 meters cubed per kilogram. So that's going to be 5 meters cubed per kilogram minus 1 meters cubed per kilogram. And a kilonewton times a meter is obviously a kilojoule, and then I have divided by kilograms, so it's going to be a kilojoule. It's going to be in kilojoules per kilogram here. So lowercase, this is lowercase w, 2 to 3 is equal to this. And that's going to be minus 4, sorry, this was wrong, right? V3 was 1. This is why I needed to have my sanity check to remember if I was doing things right. So this should have been 1 minus 5, because state 2 was at 5 and state 3 is at 1. Okay, very good. So this is negative 400 kilojoules per kilogram. That's what we're going to get. And now we're going to need to think about this for a second. So up here, why was delta U equal to 0? I don't know if I did a good job of explaining that. I'm going to do a better job right now. Why was delta U equal to 0? Well, it's an ideal gas. So it's an ideal gas. And recall that for an ideal gas, delta U is equal to CV delta T, right? I mean, I know we have to make the assumption that it's constant or whatever, but that's essentially the case. It's going to be CV delta T. And it doesn't end up mattering anyways, even if CV is not a constant, because remember that there's an integral there. Okay, and when you have an integral, if the endpoints do not change in the integral, it always evaluates to 0. So in this case, even if this was not the case, we still, the logic would still hold. And basically T1 is equal to T2, so that means that this has to be equal to 0. Excuse me. If there's no change in temperature, then delta U for an ideal gas. If there's no change in temperature for an ideal gas, then delta U has to be 0. Okay? So I should have explained that better the first go round, but now we can understand why that is the case. Now, in this case, delta U, there is a change in temperature. It's not an isotherm that we're operating on. So there could, in fact, be a change in temperature, a change in internal energy. So we'll get good practice here. So in order to get this change in internal energy, we're going to need to go to the tables. So you were wondering, why am I using the tables? This is a good point for us to do so. Okay, so we don't know what the temperatures are. This should be T2 and T3. We don't know what the temperatures are, but we do know that it's an ideal gas. So we can use those facts to help us. So P2 V2 is equal to R T2, and P3 V3 is equal to R T3. And so what does this tell us? This means that P2 V2 over R is equal to T2, and T3 is of course equal to P3 V3 over R, because it's an ideal gas. Okay, so these facts are going to be true. And R, this is for air, I believe. Let me just go up and remind myself. Yes, this is for air. R for air is equal to, again, I'm going to go to that table, but remember, you can actually divide out by M, R bar by M. We can use that fact and use table A1. But in this case, I'm just going to go to that table from section 3.1 from section 3.11 in your textbook. That's where I get the R for air. Okay, and when I do that, then I find T2 is equal to, well, I'm going to want this in terms of kilojoules, so I'm going to, again, I'm going to use 10 squared kilonewtons per meter squared. That's pascals, right? Kilopascals times 5 meters cubed per kilogram. That was my volume that was up here for state 2. And divide that by 0.287 kilojoules per kilogram times Kelvin, and that comes up with T2 is approximately equal to 1742.16 Kelvin. And doing the exact same process, we find T3 is also approximately, is approximately 348.43 Kelvin. And so we can keep going for this problem now, because we now have the values of these temperatures. Okay, so I need to find U2 and U3. We can do that by going to table A22, and we find, unfortunately, we don't have exactly 1742. So we find, let's call it TA is equal to 1700 on the table. TB is equal, this is a table for air, as an ideal gas. We find TB is equal to 1750. These are Kelvin here. And UA is equal to 1392.7 kilojoules per kilogram. And UB is equal to 1439.8 kilojoules per kilogram. And notice that what we want is 1742.16, right? That's why we need to do this. So we're going to need to do some interpolation. So we need to get, this is going to be the slope, not to be confused with the mass, is equal to, well, we want to find the U, so it's going to be 1439.8 minus 1392.7. These, of course, are going to be kilojoules per kilogram, divided by 1750 minus 1700. And this comes out to be approximately 0.942 kilojoules per kilogram times Kelvin. And that's going to be my slope. And, of course, then U2, in this case, is going to be equal to, well, M times T2 here, because that was what I needed. T2 minus one of these, it doesn't matter which. I'll just do the TA here. Minus 1700 plus the value that goes along with that, which is 1392.7 kilojoules per kilogram. This is going to be in Kelvin, of course. And T2 was 1742.16, so I'll let you substitute that in. But what I get is that U2 is approximately equal to 1,432.4147 kilojoules per kilogram. And that makes sense because this was almost 1750, right? So this should be almost 1439.8. Makes sense. Okay, same process for U3. And what I find is that U3 is approximately equal to 248.8896 kilojoules per kilogram. Okay, so I did interpolation here. And, if you get numbers slightly different than mine, that's okay. As long as they're close, right? That's basically what we're looking for. So delta U is equal to 248.8896, right? Because it's going to be U3 minus U2 minus 1432.4147, which is going to be equal to minus 1183.5246 kilojoules per kilogram. Okay, so then recall that way back up here, I didn't do the energy balance. But again, we're going to ignore kinetic energy and potential energy effects. So we're going to say that delta U has to be 2 to 3 has to be equal to Q of 2 to 3. These are lowercase values, right? minus W of 2 to 3. And that means that we can find Q of 2 to 3, because we're going to need the Q values, right, to figure out how much Q went in, is going to be equal to delta U of 2, 3 plus W of 2, 3. And that was equal to well, W was negative, right? As we recall up here, somewhere up here. W23 was minus 400 kilojoules per kilogram. So that means Q 2 to 3 is equal to, well, delta U is minus 1183.5246 kilojoules per kilogram. And then the W was minus 400 kilojoules per kilogram. So this is equal to minus 1583.5246, again, kilojoules per kilogram. That's what Q23 is. And then for 3 to 1, okay, going from 3 to 1, notice that the volume does not change. So immediately you should be thinking, if the volume does not change, there can't be any work there. And so now what that means is, but it's not constant temperature, right? It's not an isothermal process. So that means that we can't make delta U equal to 0 again. That's not going to work. So energy balance, let's jump right to the energy balance. Delta U 31 is going to be equal to Q 31 minus W 31. Since volume doesn't change, W31 equal to 0 kilojoules per kilogram. These are lowercase values, right? So it's going to be in kilojoules per kilogram. And that just means that delta U31 is going to be equal to Q from 3 to 1. And so this is a fun little one. We actually have already done the work that we need to find delta U31. This is going to be equal to U3 minus U1, but U1 is going to be equal to U2. And why? Because this was isothermal, right? So remember, from 1 to 2, one to 2 is isothermal, which means delta U is equal to 0, which obviously implies U2 minus U1 is equal to 0, which implies U1 and U2 are equal. Okay, so we know that this is the case. So we already know both of those values. We had U2, we had U3, and we had U2. So that means that delta U31 is equal to, but this time it's going to be sort of the negative of the previous step, right? Because the endpoint is now are now swapped. 4142 minus 248.8896 kilojoules per kilogram. which equals 1183.5246 kilojoules per kilogram, which means the Q 3 to 1, lowercase q, sorry, 3 to 1 is equal to 1183.5246 kilojoules per kilogram. Okay, so let's recap. We got this, and we had the Q somewhere up here, way up here, I guess. For this one, Q12, Q23 and Q31. So let's actually write those all down. We know for 1 to 2, W 1 to 2 was equal to 804.719 kilojoules per kilogram. Q from 1 to 2 was equal to 804.719 kilojoules per kilogram. For 2 to 3, W23 was equal to minus 400 kilojoules per kilogram. Q from 2 to 3 was minus 1583.5246 kilojoules per kilogram. And 3 to 1, W31 was equal to 0 kilojoules per kilogram. And Q31 was equal to 1183.5246 kilojoules per kilogram. Now recall, eta is equal to the net work of the cycle and divided by the amount of heat that went in, right? Not the total amount of heat, but the amount of heat that went in. So this is not net. So that means that Q in is only the stuff that went in, which is 1183.5246 plus 804.719, and this is going to be kilojoules per kilogram. Okay, notice I ignored the negative one, right? Because that's Q out. So recall our sign convention, that's Q out. So this is equal to, this ends up being equal to 1988.2436 kilojoules per kilogram. And the work of the cycle is all of those added together. And this is obviously specific work. It doesn't matter if it's specific or just regular work, right? It ends up being the same thing because they're ratioed by the mass, both of them. So those things end up canceling out when we divide them out. So we don't care about the fact that that it was the specific work. Minus 400 plus 0, right, kilojoules per kilogram, which is equal to 404.7190 kilojoules per kilogram. And so now our efficiency, eta, is equal to 404.719 divided by 1988.2436. I'm not going to put the units because the units obviously cancel, and we get about 0.20356, I think. And so approximately 20% efficiency. And believe it or not, that's actually a pretty decent efficiency. That's all that I have for this video. Hope to see you again soon.